Hello, everyone. Today we have Kasia Rejzner joining us. Kasia is a professor of mathematical physics at the University of York, and they're currently the president of the International Association of Mathematical Physics. Kasia works in algebraic quantum field theory, particularly using perturbative approaches, and has authored the book Perturbative Algebraic Quantum Field Theory: An Introduction for Mathematicians, as well as co-authored a paper with James Fraser on the history of perturbative approaches in pAQFT. So I'm very looking forward to what Kasia has to say on perturbative algebraic QFT in this talk. Kasia, please take it away.
Thank you. Thank you so much for the invitation. Let me start with a short introduction into what is mathematical QFT and what problem we are trying to solve. And then I want to say a few words about this particular approach I'm working on. So on a very sort of fundamental basis, quantum field theory is trying to solve the problem of combining quantum mechanics with special relativity. So, the original question was asked a long time ago, not so long after quantum mechanics was actually introduced. And the question was actually motivated by quantizing electromagnetism. So it was motivated by the try to develop QED, is what happens if you have special relativity effects together with quantum mechanics effects. And sort of, now the flagship experiments that probe quantum field theory combine these two because one looks at what happens to particles, quantum particles at high velocity. So this is, for example, the LHC experiments, where you accelerate things to a very high velocity, collide them, and see what comes out. So that's the sort of primary way physicists have been testing quantum field theory up to now. So we have these two frameworks, special relativity and quantum mechanics, and let's look what's in them. So what type of objects do we want to describe? So in special relativity, we have causality, we have the structure of Minkowski spacetime, notions of future, past, and space-like separation. So we have all these things coming from the structure of the Minkowski metric. And from quantum mechanics, we have observables, and they will want to think about observables as elements of a certain operator algebra. They're acting on states, on the space of states. Then to connect with experiment, we want to compute things like expectation values, correlations, and finally, important notion of entanglement. So all these things have to fit together in one box. And when people tried to do that, there were immediately obstructions. So if you try to, like, very naively, say, okay, so I have those quantum operators that are localized somewhere in spacetime, so I'm working with operator value distributions mathematically, then things go wrong very quickly, essentially, when you try to make sense of multiplying such operators at a point. And this problem was the problem of ultraviolet divergences. And as I said, it appeared very quickly into development of quantum mechanics. So the worries about consistency of QED, quantum electrodynamics, as a quantum theory appeared already, in famous Dreimaner-Arbeit, and sort of serious concerns were raised in 1930s, 1940s. So really, it's not a new problem in a way. Then, there were more issues, actually. So using perturbation theory, one could still try to, compute things despite these apparent divergences. But then it turns out, well, the standard sort of method of computing things was using Feynman diagrams is a certain perturbative expansion to compute, say, correlators of observables in quantum field theory. And then in this perturbative expansion, well, the parameter is h bar, corresponds to something called the loop order. So you want to expand over diagrams with more and more loops, essentially. And then it turned out that, well, if you go to higher orders, there's more and more diagrams. And that number of diagrams is actually growing very fast. It's growing factorially, which means that this cancels like the sort of coefficient in this perturbative expansion, which well, is 1 over factorial. So effectively, if you want to compute something in quantum field theory, you get this infinite power series in h bar, and this series doesn't converge. So somehow, well, that was another worry, that maybe, well, a sort of naive order by order computation doesn't really give you a convergent series. So that these were concerns raised in the 50s, for example, by Hurst and Turing. It gets worse. Okay, so apart from that, there are also infrared divergences. So this comes, so the UV divergences I mentioned before, they come from the behavior of various integrals over momentum space at large momentum. And here there are also problems at small momentum, large distances. And essentially, this is the problem of the fact that, Minkowski spacetime has infinite volume. So there are various limits where you want to go to infinity in like the range of the interaction, for example, again in QED, because, well, electromagnet is the Coulombic interaction has a long tail, is long distance, and that causes even more problems. And these divergences are called infrared divergences. Okay, again, this was already quite bad. Now, there is maybe less known type of divergences that we don't talk about that much in physics textbooks. They were discovered by Stückelberg, again, in the 50s, so relatively early on in development. And these have something to do with, well, if you try to take the interaction picture seriously, and then you want to compute something like a Hamiltonian on a thin slice on a Cauchy surface, so like time zero, fixed time surface, then you get into even more problems. So a sort of sharp cutoff in time causes an entirely new type of divergences, which are called surface or Stückelberg divergences. Okay, so quite a number of different issues that appeared with formulation of quantum field theory. Okay, so there were essentially two ways of going around it. So one way was to, well, let's forget this whole business. Let's start top down. Let's develop axiomatic approaches where we can first like try to guess what quantum field theory is, put some axioms that it should fulfill, and then analyze like various solutions to these axioms, so various models, and then work with that and forget that whole business with sort of quantizing it the way we quantized quantum mechanics, so starting from a classical system. Okay, and the first set of axioms that were developed were the Whiteman axioms. So that's what I already mentioned. The problem of localizing operators could be described using operator value distributions. And Whiteman axioms are, well, sort of physical axioms, physical properties imposed on a collection of such operator value distributions that's supposed to describe physical observables. Okay. So White-Mann axioms work intrinsically on Minkowski spacetime. Now, many calculations are more conveniently done upon Wick rotation. So when passing to, formally passing to imaginary time and working on the Euclidean signature. And then you can actually formulate things in terms of correlation functions in the Euclidean signature using Osterwalder-Schade axioms that guarantee that upon Wick rotation back into Lorentzian, you get a theory that satisfies the White-Mann axiom. So it was a sort of technical improvement there. And finally, Haag-Kastler axioms, so axioms of algebraic quantum field theory, where instead of operator value distributions, one works with operator algebras that are somehow localized in spacetime. Okay, so these were the various axioms. Now, at the same time, people started also another approach to, dealing with these various QFT issues. So instead of, doing top-down approach, they went bottom-up. So here is what we know about QFT. Here are the issues. So let's focus on solving the issues and develop a framework that works for perturbative QFT. So let's assume that we want to do perturbative QFT and then start from there because we know how to do it. People do computations. Let's try to put a mathematical framework for that instead of coming with something entirely different. Okay, and for a long time these were actually working in parallel. Initially, I mean, I'm sure there was some exchange, but things sort of went apart for a bit. So only in the 90s, so really recently, these were somewhat combined in the approach of perturbative AQFT, which is the approach I'm working on myself. And this brought these two strands of mathematical QFT together and turned out to be a very powerful tool. Okay, so yeah, I will explain some main concepts of pAQFT. And towards the end, if there's time, I can also say how this can be used for non-perturbative results in the future. Okay, so here is a picture from my paper with James Fraser, which I think very nicely illustrates what happened with mathematical QFT. So these two directions, axiomatic QFT and causal perturbation theory, they kind of focused on curing different divergences and sort of different fundamental issues. So axiomatic QFT focused on large order divergences. So, let's not use those formal non-convergent series. Let's do something better. Let's not try to multiply operator value distributions at the point. Let's do something better. And this is where these White-Mann Haag-Kastler axioms come in. Causal perturbation theory kind of, decided to just bite the bullet. There are those large order divergences, so we will work with series that are formal, that don't converge. These are asymptotic series, but let's try to solve other problems that we can. So, for example, surface divergences and ultraviolet divergences are addressed in that frame. Then they kind of both merge together, so learned from each other, and hopefully this is going to continue. Okay, so algebraic quantum field theory is the main approach I'm interested in. So let me say a few words about how this works. So, it starts with the following. So we want to localize our quantum operators, quantum algebras in spacetime. So initially was developed on Minkowski spacetime. So to a bounded region O in Minkowski spacetime, we assign the algebra of observables that can be measured in O. Now, okay, so here this uses words, observables, and measured. Obviously, you think first about quantum information theory, measurement theory. Surprisingly, despite the sort of conceptual idea that yes, these should be things that are measured in a region, it took a long while again before the actual honest theory of measurement was developed for this framework. This is not going to be a content of this talk, but just to flag it, it can be made sense, this statement that these are actually observables that can be measured. But that's a whole, lot of additional conceptual work that was done, essentially by Fuster and Fesch about 10 years ago. So much, much more recent than Kastler. Okay, so but coming back to the axioms. So the first axiom we want is describing the notion of subsystems. So if we have a smaller region inside a larger region, then we want this smaller algebra to be contained in the larger algebra. Oops, sorry. That should work. Okay. And then we ask for some further axioms. So the two most important axioms that I want to focus on are causality and time slice axiom. So causality, let's see if I can annotate this. Sorry, I completely lost the proficiency in Zoom. If it doesn't work, it doesn't work. Okay, maybe it does work. Okay, so if we have two regions, O1 and O2, that are space-like separated, so there is no causal curve joining them, so this is a picture, then we want the observables that are localized in these regions, not to pass information from one to the other, so nothing travels faster than light. Things can only travel on the light cone, so there is no way to pass information between these two. Hence, the corresponding operators should commute. Okay, and the time slice axiom says that if I have a neighborhood of a Cauchy surface, so again, let me draw a picture here. So here is a diamond, here is a Cauchy surface. Let's take a small neighborhood here. This is N, and this is O. Then we have an analog of initial value problem, which says that if I have the algebra associated to N, this is already enough to know everything about all the operators in O. So actually, this shouldn't be isomorphic. This should be equal. So A of O is equal to A of N. Because, well, we know that A of N is contained in A of O, but this is much stronger. Okay, so let's start with these. And there are more, but these are actually sort of most important like physical considerations before we specify like distinguished states like vacuum or properties of the vacuum. Now these also generalize to curved backgrounds, so we don't have to work on Minkowski. We can go to something more general, so we can actually even mix in some GR effects. So we can study things like early universe or black holes. And in this framework, instead of assigning algebras to subregions of a Minkowski spacetime, we can work with like a whole class of spacetimes with certain properties, and to each spacetime assign an algebra of observables. Okay, and then sort of mathematically, right? So we assign algebras to spacetimes, and we assign algebra maps to embeddings of spacetimes like that. And we have this whole covariant story about how this assignment works. So if you're interested, there is a nice way of formulating this using categories and functors. Okay, so we are now already sort of firmly in the AQFT framework. Now, just to try to again connect back to perturbation theory. So clearly, it feels like this is a very different setting from sort of perturbative QFT approach with renormalization and so on. And this tension was actually pointed out many times. So sort of on the other side of the divide, a very sort of traditional approach to quantum field theory by practitioners is Wilsonian renormalization. So this uses entirely different concepts, it seems. So there are scales, the notion of renormalization, there's the perturbation theory, but it has concrete tools for constructing models that AQFT as such doesn't really come with. And again, you think like, okay, can they fit together? Can one learn from each other? Can they even talk to each other? Do they even describe the same theory physically? And surprisingly or non-surprisingly, I mean, I guess from a mathematical side, maybe it's completely non-obvious that these things can fit together, but they do describe the same physics. So yes, you can actually connect the two. And this is, again, happening within this perturbative AQFT. So there are concepts like Einstein causality, so this commutation at space-like distance, but also concepts like renormalization, perturbation theory, and yes, concrete tools for constructing models. Now, why should you care if you're not interested in foundations of quantum field theory? Well, it actually is useful to have a clear conceptual framework, and you don't have to worry about, is this the right thing or is this the right thing, and you want to compute something, and is this actually computing what you want, and so on. So it's very hard to work with a physical theory which doesn't have a clear conceptual framework, because then you can argue for a long time whether what you're doing is the right thing, and there's hardly anything to refer to. I mean, there's of course the physical intuition, but there could be different ways to describe mathematically the same physical intuition, and you want to be consistent when you're thinking about the big picture. And that turned out to be very useful in QFT on curved spacetime when it seemed that there were many ways of making sense of quantization of field theory in such context, but all these different ways kind of they live in one conceptual framework of pAQFT. Okay, so who came up with this idea? Well, that's always a complicated question, and as many things in the history of mathematics and physics, there were many people who contributed to it. So this was a collaborative effort. So here are the ingredients. So there is deformation quantization, which kind of is, that is a field of its own in mathematics, kind of way to think about quantization in terms of deformation of products. And that was applied to this problem of quantizing free theory in this new conceptual framework. This was done by some combination of names, Brunetti, Deutsch, and Hagen in early 2000s. Then renormalization that used this causal perturbation theory approach, which has been developing since the 70s, is due to Epstein and Glaser. So that merged these two paths that were going in parallel for a while. And then a generalization to gauge theories is much more recent. It uses methods of homological algebra. So first it was applied to Young-Mills theories by Holland, and then generalized to arbitrary theories with local gauge invariance by Hagen and myself in 2011. And finally, when it was essentially enough to put things together in a conceptual framework, there is a book that was already mentioned at the beginning of the talk that I wrote in 2016, and multiple reviews by various people. So at this point, there's a lot of research to actually learn this framework if you're interested. Okay, so what are the axioms? I mean, it is an axiomatic framework, but an axiomatic framework that also comes with a toolbox on how to construct model, which is different from the standard, say, Whiteman or Haag Kastler. So the idea is to modify those axioms I mentioned before by allowing these local algebras that you assign to regions of spacetime to allow for formal power series in H bar. So instead of having, honest to goodness, say, C-star algebras or von Neumann algebras, I have these formal power series in some, relatively nice topological algebras. But yeah, there is this notion of formal power series because we are still not really facing the large order divergences. We want to keep things like causality and time slice axiom. And this worked really nicely for the scalar field. So one can construct models in this sort of slightly weakened framework relatively straightforwardly. I mean, combining these methods of Epstein-Glaser and things I mentioned on a couple of slides ago. But then for gauge theories, then you have to further weaken those axioms. So need to allow for a bit more freedom. So I mentioned homological algebra. Mathematically, there is like the whole theory of allowing for working with chain complexes in order to describe concepts like gauge invariance. So for sort of the precise statement of these axioms, I refer you to my paper with Owen William from 2020. So it weakens further this idea that, we already have formal power series, but let's also do chain complexes. And then again, causality and time slice axioms are there, but they're also slightly weakened. So the way you want to think about it is that there is some notion of gauge invariance, and things are true up to like gauge invariance. So they're true for gauge invariant observables. Okay. And then, so things that fail, this notion of subsystems, that was one of the axioms. So it's called isotony, that fails. So one has to replace it with a different way of building global structure from local data. Okay, and some pretty heavy mathematics coming into it. And then there is a further generalization that allows for even more freedom and kind of the usage of more sophisticated mathematical tools, which is called homotopy QFT and was formulated by Benini and Schenkel. And it's also, active area of research. So this is the current state of the art in terms of axioms. And now the other sort of side of the story is constructing models in pAQFT. And so the main idea is that those local algebras assigned to regions of spacetime, are generated by something called local S matrices. We'll give some intuition about it later. And these are labeled by, well, essentially something that models observables, local observables, which in this case is local compactly supported functionals. So just to give you maybe some very quick intuition here, things like integral phi to the fourth smeared with some test function, this would be a local compactly supported functional. Okay. And so, as I said, I mean, this can be interpreted as some interaction. So like, for example, phi to the fourth with a cutoff. So the fact that you have a smearing with a test function is important. And this is essentially used to going around Haag's no-go theorem about using interaction picture in quantum field theory. So one works with an interaction with a cutoff and then constructs the theory and then takes this cutoff away at the end. There's a limit called the adiabatic limit. And yeah, this essentially goes around this problem. So one can, morally speaking, use the interaction picture, but you have to just be careful about the order in which you take limits. And I think this is a nice example of, where no-go theorems become yes-go theorems. So you just have to find the right way of doing things. So you have to find the right concepts. In any case, we are interested in local algebra, so this limit, for all practical purposes, doesn't even have to be taken. So one can actually just focus on things that can be measured locally. And the construction itself is based around two products. So there's the quantum product that, in quantum mechanics, right, there's this non-commutative product that, describes all the sort of non-classical effects, right? Operators don't commute, and hence good things happen. But there's also another product, which is commutative, and it's called time-ordered product. And this product appears as the consequence of using path integral to compute things to describe these observables in the interaction picture. So you can think of time-ordered product as something that directly arises from the path integral. And well, we know that path integral has its own issues. But here, in fact, this time-ordered product is a well-defined concept, even if path integral itself isn't. So it's as much as it's left out of path integral without actually thinking about it as an integral. So just taking the algebraic structure behind it. Okay. So if I want to build a model in pAQFT, I start with a globally hyperbolic spacetime. Being globally hyperbolic, it means initial value problems make sense there. And well, one thing about the globally hyperbolic spacetime worth noting is that there are no closed causal curves in such spacetimes, which means, well, unfortunately, time travel is not possible. So the notion of causality is important in that framework. Now, then you have to specify the space of fields, so choice of objects you want to study. So it could be scalar fields, vector fields, tensors, whatever you want. And again, to put some mathematics into this, this configuration space is a space of smooth sections of some vector bundle over M, typically. Here are some examples. So for the scalar field, it's this. Okay, maybe I can use a better pointer. Oh, no. Maybe this one is better. And for Yang-Mills, these are one forms valued in some Lie algebra. And finally, we can even do effective quantum gravity, where configuration space consists of metric perturbations. As for dynamics, we use some modification of the Lagrangian formalism, which, however, is covariant. I mean, we don't really need to split into space and time explicitly. This works fully covariantly, so it's kind of consistent with the spirit of general relativity. Okay, so let's start with those observables, and I'm going to go a bit more technical in this last part of the talk for those of you who want to be, more precise about what we're actually doing here, and just tell you some more mathematical details. So first of all, classical observables. So these are functions on the configuration space. So what does it mean to measure classical observable, right? I mean, you have some configuration of your field, you make a measurement, you get a number. So these observables can be described as functionals. Classically, you essentially think of them as real values. However, here in this context, it makes more sense to allow for things to be complex valued. Okay, so yeah, that's that. Sorry. Okay. We fixed the spacetime for the rest of this talk, so let's not write M every time. Just have in mind that this can be done on any background, so Minkowski, black hole, De Sitter, Friedman, Robertson, Walker. So a lot of interesting physical situations. Now I want to localize those functionals. So there is a notion of support. And support essentially describes the region of spacetime such that, in that region, a functional is sensitive to field perturbations in that region. So it kind of characterizes where this functional can be used to measure the field perturbations. This is still classical. And then in particular of interest are the local functionals. So they can be written as an integral of a function of the field and its derivatives at a point. Okay, and now the dynamics, I mentioned Lagrangian framework. So we are using something called generalized Lagrangian. This is Lagrangian with a cutoff, again, as I said, to avoid problems with Haag's theorem. So it's a function from the space of cutoffs, so the space of smooth compactly supported functions into locals. And here are examples. So you take your favorite Lagrangian density, let's say free scalar field, you multiply it with the cutoff, and here we are. Similarly, this is the Lagrangian for Yang-Mills, and this is the Lagrangian for gravity using Einstein-Hilbert action. Okay, and then you want to have some notion of dynamics. So, you want this actually to be independent of the cutoff. Now, fortunately, it is. So here is the notion of Euler-Lagrange derivative. So the way you want to think about it, so you perturb your field by psi in the direction of psi, and then choose this cutoff f in such a way that it's equal to 1 on the support of psi. And then this difference of the Lagrangian perturbed and non-perturbed doesn't depend on the choice of f of this cutoff, as long as it's equal to 1 on the support of psi. So this is a direct consequence of locality. And then infinitesimally, this difference gives you Euler-Lagrange derivative using difference quotient. So this Euler-Lagrange derivative, denoted by dl, it's actually one form on the configuration space. Okay, and the field equation can be written very in a simple way. It's the condition that this one form vanishes on a given phi. Well, if you write this explicitly, this condition turns out to be a differential equation, as you might expect. So these are the usual field theory equations. And we assume that, well, we're in Lorentzian signature. Nice equations are hyperbolic. So here I assume normally hyperbolic, meaning it's essentially a wave equation, right? A wave equation maybe plus something of lower order. Okay, and here is some bunch of technical ingredients into how to construct models given that. So we have some normally hyperbolic equations. So P is, for example, the Klein-Gordon operator. And then for such equations, we know about the existence of some nice object. So P has some distinguished inverses. So they're retarded and advanced green functions in such situations. So, well, green function is an inverse, essentially. And being retarded or advanced, this has something to do with support. So if we have some compactly supported function, then the retarded green function would propagate the support to the future. Advanced green function will propagate the support to the past. There's some causal structure already entering at this stage. And then one uses the difference of these two, retarded minus advanced, as the commutator function. So this will give us the commutator of operators. And then, so that serves as the anti-symmetric part of what will become the two-point function of the theory. And there is also a symmetric part, which is chosen in such a way that this whole thing, well, mathematically, it has a nice singularity structure. Okay, so that's one ingredient, is this two-point function. And then another object you can construct from these pieces, so retarded and advanced green function, as well as the symmetric part, is the Feynman propagator. So these two ingredients, so the two-point function and the Feynman propagator, will allow us to introduce those products that we need to describe our theory. Okay, so again, in practice, how do we do that? Well, first we define time-ordered products using this Feynman propagator of functionals with disjoint supports. So this avoids for now dealing with UV divergences. And this is in a way, if you've seen some quantum field theory in the past, this is actually very simple. So you assign derivatives to sort of vertices, and then you assign the Feynman propagators to the edges, and then you contract this to vertices that correspond to your functional. So, for example, that would be like phi to the fourth interaction. And then the way this formula works is that you contract these various edges using the Feynman propagator, and that's how you compute these expressions. So the combinatorics is very much familiar. But then there is a question of what you do at coinciding points. So what if you want to extend these things to functionals with arbitrary supports? And this is exactly where Epstein-Glaser renormalization and causal perturbation theory enter. So these methods allow you to deal with these UV divergences in a mathematically rigorous way. And the idea is that, well, you can construct those time-ordered products order by order using some sort of recursive procedure, inductive procedure that on the mathematical side uses extensions of certain distributions. Okay, and then one of the crucial properties that one wants to preserve with those extensions, sort of one of the things codified in Epstein-Glaser axioms, is causal factorization property, which tells you that if you have a bunch of functionals with supports that are not later than another bunch, so let me again draw a picture. So you have like some functionals here, and then there are some functionals which are clearly space-like or in the past. Then the time-ordered product factorizes. So you take a time-ordered product of these guys and then star it with time-ordered product of these guys. This way you can actually, in practice, construct the higher orders from lower orders in a recursive fashion. Okay. So let me maybe quickly cover that as well. So what is actually important in this Epstein-Glaser renormalization? So we never talk about infinities, okay? So there's no subtract one infinity of another infinity and get a number. This is not a good thing in mathematics. So instead we talk about extensions. So we have some quantities that we know, let's say, everywhere outside the origin of Minkowski spacetime, or everything outside of the diagonal, and then we want to extend. So we have some concepts which are a priori defined, and then we want to extend the domain, and this is what renormalization does. This is much cleaner than talking about, a priori ill-defined concepts with infinities and then trying to make sense out of it a posteriori. Okay, so that's the idea of these extensions, but of course, devil is in the detail. These extensions are not unique, so we can describe their non-uniqueness actually very precisely. And again, this is the advantage maybe of this framework, that the problem of defining physical quantities is kind of separated from the problem of studying their uniqueness. And this non-uniqueness is then governed by renormalization group. So renormalization group describes the non-uniqueness of these extensions. Okay, so with that in mind, you can use those time-ordered products, given choice of time-ordered products that you have obtained, to define the S matrix as time-ordered exponential. And then the causal factorization property gives you like another nice sort of way of factorizing things if you have V1 and V2 with supports that are either space-like or one comes before the other. And yeah, so these S matrices are the sort of fundamental objects. So then local algebras are generated by those things. Okay, if you want to, again, connect with traditional perturbative QFT, as I said, this is the picture with Feynman diagrams. So like in your computation, you're trying to construct those distributional extensions. Very quickly, you arrive at problems where you, for example, have a loop in your computation, and then you have to define this sort of expression that corresponds to this Feynman diagram by extending certain distribution on M squared. Yeah, and these time-ordered products can be then like all bunched together, and you define a map called time ordering, which you can connect to the path integral. So this time ordering map formally would correspond to taking convolution with the Gaussian measure using path integral. So the right-hand side of this formula is heuristic. The left-hand side is actually a well-defined concept that you can construct using Epstein-Glaser renormalization. Okay, more things. So S matrix is time-ordered exponential. Time-ordered product has this, well, it's time-ordered version of the quantum star product, in the sense that if you have like things with support arranged this way, so G comes first, F comes later, then it's equal to the star product. And if you have the opposite configuration, then you just change the order of G and F. And one last thing I wanted to mention in this context is the main theorem in renormalization. So more precisely what it means to have this renormalization group measure the non-uniqueness. So this is a subgroup of the group of maps from formal power series in local functionals to local functionals. And what it does is that if you have two different prescriptions for time-ordered products, then these S matrices, so these time-ordered exponentials, are related by an application of this map. So Z of F essentially corresponds to changing the coupling constant or adding counter terms in your interaction in your observable F. Okay. Okay, so I think maybe it's time to finish now, but let me just say that there is a non-perturbative setting. So you can take these objects, those as matrices, again, as abstract objects, as abstract elements of some operator algebras. And there is a way to construct C-star algebras that, satisfy the stronger version of Haag Kastler axioms for interacting theories that was introduced by Buchholz and Hagen. Then it was generalized, further developed by Brunetti, Deutsch, Hagen, and myself, and it's still under development. So we're hoping to get some new interesting perturbative results. In particular, this paper about unitary master word identity, we analyze things like anomalies, symmetries, and that was for global gauge symmetries. We're currently working on the project to do it for local gauge symmetries. Okay, so the rest is extra material, and let me thank you for your attention.
Excellent. Thank you so much, Kasia. For those joining us, do we have any questions?
Hi. I have a fairly basic question about algebraic QFT, and that is, how do you define a bounded set in this Minkowski spacetime setting, or in this Lorentzian spacetime metric?
Oh yeah, so bounded in Rn is actually easy, but in more general spacetimes, you look at something which is relatively compact. So what replaces bounded sets is you take things, open sets whose closures are compact. Does it make sense? So like compactness makes sense on curved spacetimes, and so that replaces the notion of boundedness.
Thanks.
So things that don't go too far to infinity.
Do we have any other?
Yeah. Hi. Can I ask in sort of more practical quantum field theory, you talk about scheme dependence and scheme independence. Is that does that correspond to your renormalization group.
That's right. That's right. So, like, you can think of, so first of all, you can think of all these regularization schemes as giving you particular extensions. So these particular definitions of time-ordered products, say T tilde, and then the Stuckelberg-Peterman renormalization group gives you a way to translate between one and the other. So I think it's a nice way to kind of talk about scheme independence, because it has all schemes together. So what you need to do is, let's say for dimensional regularization, you show, oh, this is how this maps into Stuckelberg-Peterman renormalization group. And then if you want to go to another regularization scheme, then you can construct the corresponding map Z. And this has actually been done in practice for, commonly used regularization schemes.
Yeah. So the scheme invariants, which would be, some sort of more physical things, they are like this construction modulo the renormalization group somehow.
That is correct. Yes. Mm-hmm. Yeah.
Okay.
Thank you.
Thanks.
Excellent. Do we have any remaining questions? Okay, I'll quickly ask a question of my own then. Mm-hmm. You mentioned that there was some current work done yes. for non-perturbative approaches as well. What are the current challenges facing perturbative algebraic QFT, I guess, and what are the directions that are being taken, both perturbative and non-perturbative? Okay, so like non-perturbative, the challenge is to construct states. So you can construct local algebras, and this works, and this is great. But the challenge is to understand how to construct, say vacuum states or thermal states for those interacting theories. But that's a very difficult problem, because, I mean, if we knew how to solve it, then we could actually rigorously construct, say, Young Mills in 4 dimensions, which is one of the millennium problems. So let's face it, this is not going to be easy. So that's one big open problem. There is also the question of understanding measurement, and more recently quantum reference frames in this context. So this is both in perturbative and non-perturbative. And again, it's not a new question, but it's only recently that this gained some traction. And other things in perturbative QFT, understanding how to quantize things on spacetimes with boundary. So instead of, say, like, I have an open diamond and consider the theory associated to that, what if I take the diamond with the boundary? And this, I mean, this has some sort of bearing on things like, quantum gravity, and people think about approaches to quantum gravity using, building things from these pieces and gluing them along boundary. And this has also some, well, actually, there's one problem with these divergences I didn't mention at all, which is the infrared problem. This is not really solved by Epstein-Glaser or directly by pAQFT, because this is a local construction, but it's of course an important question what happens globally. So that's another big construction site. So quite a lot to do still. Okay, thank you. If there are no more questions, then I guess we can wrap up here. Just doesn't look like there are any more questions. Okay, thank you very much for
thank you.
Joining us, Kasia, and talking.
Thanks for having me. Bye.